So we are actively in a detached model of Hudson Yards Tower A, and you can see we're in the lobby floor plane here. And to give you a sense of scale, you can already see on this side core area here how many elevators we have versus passenger elevators, center core elevators, and then down here is the retail podium connection that's happening here. So if we start to look at these elevator families and how all of these needed to be organized, I'm going to move into the family component here. So these family components have a series of 3 nested families within them. I'm going to go ahead and go down into the lowest tier and work my way backwards just as an organizational roadmap for where we are. So if we start here at the lowest tier, this is our basic 2D family. So we have a simple 2D family that, because of the scale of this building, we are very careful of what is a 3D family versus a 2D family because of how big the model is. So what we did is we took this 2D family and are moving it about an invisible 3D line. So really it's just a 2D graphic that I then assign an area of usage. So the family starts here on this level, which is our lowest tier, where you can see this is the individual lines that are creating the doors and the cab and the opening, and then setting up a series of shared parameters that are flexible so that when I type in these dimensions, it flexes and moves with what I need it to. So you can see here that we have our base parameters, that as we move into the next tier, through our shared parameters, we are going to be passing these all back to what our original 2D cab family is. So we complete this 2D cab family. We then move into the second tier. And on the second tier, we have actually a combination of several families. You can see we have our counterweights, we have our guides, we still have our elevator cab, and now we have our shaft. If you click on some of these, you can start to see over here how many different families are nested in here and what all of their sizes are. And so what we did is that everything, again, is passed back to that original cab, and then there's new ones created in this tier so that everything is still flexible, so that you can see as long as I have a center 2-door speed elevator cab, my shaft width can be 12 feet, it can be 10 feet, it can be 15 feet, and we're going to control that in the type parameter rather than having an entire new family. So we're cutting down the amount of work that needs to be done. You can see here on the parameters that there's several more shared parameters here that were in our first tier. Things like cab width come into play, things like the shaft width and depth, the openings, the guide offset, door thickness. All of these parameters came from that larger umbrella planning session with the client of what did the cab need to do. As the project developed and got more and more developed, at some point we were not controlling what the thickness of this cab was, and then we started controlling it because we needed to know the thickness to know the true dimension of the inside of cab, especially for our ADA elevators and where stretcher radiuses and stuff like that come into play. But you can see throughout here that this entire family is a fully flexible family. So then the series of all of these, there's probably 4 to 5 pieces that are in here. These then get nested one more time into our top tier, which lives here, and this is the single family that then ends up getting placed in our model. If you look here at the side, you can see all of our parameters, and you can see how everything gets passed back to the family before so that we have full control over this. If we start to look at these parameters, the next thing that came into play is the PMs went through the spec and cut sheets that come from the elevator consultants, And it was desired as such from lessons learned from a previous building that we needed to be able to see at a snapshot in time on a schedule what were the specs that we were going to be responsible for, that we're going to go out to bid, so that we always knew that the level of accuracy across elevator consultant all the way to contractor was exactly what it was supposed to be. So there's a series of text parameters that are happening here, that this information is coming directly from the elevator consultant. We then have all of the dimensional parameters that are coming, again, from that same cut sheet. But then several of these, of course, are changed based on our steel tolerances, and as fireproofing changes and some of our cores changed, and the actual amount that we have in our shaft. And then we come down to our actual area of usage formulas. So once you sort of get all of those parameters, you can see the same with the nested ones, that this is a fully flexible family that is set to move in certain ways so that everything is moving correctly. One of the big things that we did is, at first when we made these families, everything was centered about this center reference line. But we came to find out that more and more often the cab was not necessarily directly centered in the shaft. So this cab width offset was one of the most important parameters that we made. So the offset of where this cab lives could change, and that basically took about 50 families down to 20, because before this existed, the cab, you know, we needed these to be placed in the core and to be able to dimension this. And if on one elevator this was 10 inches, and the very next one it was 11 inches, but everything else was the same, we wanted that to be a type parameter instead of an instance or a family, and have to have this need for more families. So we've been looking at this in plan thus far, so we're going to look at this in section and talk about that 2D family and that invisible 3D line. So the elevator that we're currently looking at is a one-door middle front opening, 2-speed, counterweight in the back, 2-bypass elevator. So when you look at this in section, you're going to start to see that this is broken up here. An area of bypass merely means that it stops on level 1, bypasses 2, 3, and 4 stops on level 5, bypasses 6, 7, and 8 stops on level 10. So we have 2 areas that it's not an active cab. It was very necessary and desired that where the active cab versus the area of bypass look graphically different, so that when I see an active cab, I see an active cab, and when I see, this is a ceiling view, but you wouldn't see the cab. When I see an area of bypass, I see the X that's going through here. So here in this section is how we were able to achieve that. So with that, we have a series of formulas that we created that you can see here. That is my overall travel distance, my lower distance, my lower bypass, middle distance, middle bypass, and upper distance. And we're basically adding a series of reference lines, assigning a dimension, an area of usage, and then subtracting one from another in order to determine what is this size. And then once we have this assembly cab here, we then create a parameter of lower distance that gets passed to the formula that we made here, so that my top elevation of lower usage minus my starting elevation will give me that lower distance that is assigned and passed back here, so that once back in my project, I'm actually seeing an active cab versus an area of bypass, even though graphic is the exact same family. So our family is doing 2 different things for us, working smarter rather than harder. So we continue that up here, area of usage, area of bypass, area of usage, area of bypass, area of usage. One of the larger things that we sort of had to figure out how to reconcile is that when you look at most elevators, your overrun technically includes the last level of usage. So how would we have an actual overrun that on our EMR levels, we would see that same X area of bypass still show our active cab, but schedule the overall overrun that would match what the elevator consultants were giving us. So what we did to figure that out is that we did add in this overrun, which is our basic standard X family, gave it a parameter of an unoccupiable overrun, and then created a new formula that said overall overrun equals the cab height plus the unoccupiable overrun. The overrun doesn't necessarily include the entire height of the floor-to-floor height that the last one is on. It only includes the cab. So no matter if your last floor-to-floor height had a floor-to-floor 13'6" or 15, that floor-to-floor height doesn't matter. It's just the cab height. So that made it really easy to make this parameter because we didn't have the variability of the floor-to-floor height that especially so often gets changed and is so different depending on the program of the space. So this allowed us to have a schedule that matched the elevator consultants with still showing graphically what the client wanted to see. And in the end, this unoccupiable distance became very, very useful, especially when looking at clash detection, space that we have up there, where the raised slab of our EMR rooms needed to go, and things like that. So this unoccupiable overrun dimension ended up being very, very useful. Let's see. And then the same thing for the pit is the pit is done in the reverse order so that the pit basically does the opposite thing of the overrun. The last thing that we added in was this notion of a graphical offset. Oftentimes in Revit, our view depths are not necessarily at 0. In our project, our view depth is a -1'4", and we need that in order to show our curtain wall facade the way that we want it to. But if you're thinking in section and I have a floor plan that's cut up here at 4 feet, and I go -1'4", and I'm supposed to be showing an area of bypass, all of a sudden I'm creeping into this area that's going to show me my active cab. So what we added there is this parameter, which is our graphic offset, that basically says, take our invisible 3D line that our 2D image is running along and offset it so that my area of usage is still the same and what it needs to be, but graphically I now have control over where this shows. So in the podium where my view depth does stop at 0, this can be set to 0 using the same family. In Tower A, where I'm at -1'4", I again can have the same family, and just in my type parameters, I'm changing what this graphical offset is. Again, bringing our total family count down from in the span of about the 50s to about only 20. So now when we look at our families, our overwhelming hierarchy of how we determine how many families do we actually need actually comes from what our naming convention is, which we have a 1-door middle, front, 2-speed, counterweight, 2 bypass. So if it's a 2-door middle, back opening, 1 speed, 3 bypass, that needs to be a different family. So that again was done in the umbrella planning conversation with the client of what were the differences that you wanted in the families versus the type.